let's start. What has happened so far is that we have tried to understand first order ODEs. Okay? What we have been trying to understand so far was that first order ordinary differential equations. Okay? The simplest case for first order differential equations was the separable differential equations. And if we have a separable differential equation, we just separate the variables and just integrate. And the solution pops up, if we can do that integration. The second step that you need to check is that if we have an equation such that this kind of a linear expression is present, okay? To solve this kind of differential equations, we just use change of variable. And for instance, select this ax plus by plus c as our z, the new variable. Then this change of variable will help us to solve that differential equation. The third step in this ladder that we are trying to build up is when we are having homogeneous equation with homogeneous functions. An equation with homogeneous functions such that this is and this is are homogeneous of degree n of the same degree, or you can equivalently turn this into y prime equal to f of xy such that f is a homogeneous function of degree 0. Okay? In these cases, this change of variable y divided by x solves the problem. By this change of variable, we have proved that this turns into a separable problem and we can solve it. The next step, I'm also going to add some things here, but first let's finish the rest of this ladder and I will just give some branches to it as well. The next one was that if we have this kind of an expression, and the problem was that if this is exact or not, okay? So the next step in the ladder was that we are asking ourselves, do we have an exact equation or not? What was the meaning of this? What was the definitions? When you're having a function, fxy, how can we calculate its derivative? What is the derivative of f? The derivative of f is going to come in this form. Partial derivative of f with respect to x, and when we are doing partial derivatives, now we are assuming that y is not a function of x. X and y are completely independent variables when we are calculating partial derivatives. So this is going to be first partial derivative of f with respect to x times dx plus partial derivative of f with respect to y dy. Okay? But look at this. If I'm working with the level curves of this kind of a function, which is going to come like this. What do I mean by that? For instance, if my fxy is this x2 plus y2. Okay? What do I have here? I can say that, okay, these are my x, y, z, and some, you see this kind of a function we have. When we are putting its values equal to some constant, okay, we are saying that, okay, for instance, what is the value when z is equal to 3? What is this intersection with this function is going to be? And if you see, it's going to be like a circle, right? In these circles, in these level curves, this happens, okay? So our tangent vector dx dy is going to be perpendicular to our gradient, which means that if I am working with level curves of this function, then I have this kind of an equation, right? We are taking just derivatives of both hand sides, okay? But why we are talking about this function f here, the problem is that, look at this. I'm having this kind of an equation, and this is very similar to what I have here. If I write this as m dx plus n dy, you will see that they're looking very similar to each other. And what was our goal? It was always this. Try to turn problem into a problem that you know how to solve it, right? So we are trying to find what is similar, what we know, and trying to make some kind of digging inside and trying to find out what's happening. Okay. No problem is this. If I have this kind of an equation, okay, can I find function f such that if I take its partial derivative with respect to x, I have this m, and if I take its partial derivative with respect to y, I get to this n. How can I find this function? This is the question. Because if I can find, then I can find a solution for this equation as well, right? For instance, if you are having this equation, okay, how do we solve it? When we are dealing with a differential equation, first question is what? What is the order of this? Okay, because we are going to also see second order and higher order differential equations, and they will have their own levels, right? First of all, we need to ask about what do you see here? Is this first order, second order? What kind of order is that? This is first order, right? This is actually dy divided by dx equal to minus x divided by y. Okay? Y prime is equal to minus x divided by y. This is that equation. So this is the first order differential equation. What we need to ask is this. Is this separable or not? So is this separable? Yes, it is separable actually. Everything related to x dx can be written as equal to everything related to y divided. So if you just integrate, we have the solution. And if you integrate, you will see that x to the power of 2 divided by 2 plus y to the power of 2 divided by 2 is equal to c is our solution. Keep this in mind. But we are trying to see what is happening with this as well. If you look at this ladder, you will see that, okay, this equation is also an equation with homogeneous functions of the same degree. X is a homogeneous function of degree 1, y is a homogeneous function of degree 1. So you can also use this change of variable in order to solve this differential equation. Okay? But this is just a simple example in order to understand what is happening. My point is that I need to come to these exact equations and try to explain what's happening over there. Okay? Now, the question is this. If I do not have this, do not have this, do not have this, how I can see that this equation is going to be an exact equation or not? Meaning that, how I can be sure that there is this function f of two variables x and y such that if I take their derivative, it is going to be equal to this. How can I know this? And if I know that this kind of a function exists, how can I find it? Today we are going to discuss about this. Okay? Look at this. What we are seeing here, what is our m here? If we are making, this is our function m. This is our function n, right? So can you please guess or take a solution out from your pocket and say that, okay, this is the function fxy such that if you take its partial derivative with respect to x, it is going to be this m. And if you take its partial derivative with respect to y, it is going to be n. Can we guess this kind of a function? In this case, maybe we can guess, but what about complicated cases? So we need to have a systematic way in order to understand what is happening beneath. Okay? This is what we are doing. First of all, we argue like this. Let's assume that such a function exists. That I take its derivative and I have this. Okay? We are also assuming that the second order partial derivatives exist and they are continuous. We are always working with continuous functions. If I have this, I can talk about some additional condition. And this is coming from Euler's theorem on equality of mixed second partial or second mixed partial derivatives. What does this say? It is saying that if you have a function, its partial mixed derivative, first take with respect to y, then take the partial derivative with respect to x. This is going to be equal to, like first we are taking it with respect to y, first with respect to x, then with respect to y, okay? These are going to be equal. This is the Euler's theorem actually. I can write this as what? Again, round of f over round of y, right? Round of f over round of y. And this is round over round y of round of f over round of x. Isn't it like this? We are just taking the second order partial derivatives. But look at that. What was our assumption here? We said that round of f over round of y must be equal to n, right? So instead of this one here, I can write n. And what about this one, round of f over round of x? We have assumed that the partial derivative of f with respect to x is equal to m, right? So look at this. If this kind of a function exists such that we have this, then we must have what? What I'm going to have is this. Let me just call this star. What is going to happen? I'm going to have equal to f. No, I'm writing it. This is round over round of x. This is n. Right? You see what is this? Round of f over round of y. We have called it n. So from n, I need to take derivative with respect to x, and from m, I need to take derivative with respect to y. If this equality is satisfied, I can say that this equation is exact. Okay? Which means that maybe there was that function f such that if I take its derivative, this is going to happen. Because if exists this kind of a function f, then I know that this follows. Okay? So this is condition for exactness. Condition for exactness. Now, let's go back a little bit. We have this kind of an equation. We would like to know if this equation is exact or not. What do we need to do? We need to check this condition. Can you please check this condition for this equation? What is going to be round of m over round of y? From the coefficient of dx, we are taking partial derivative with respect to y. If from x you take partial derivative with respect to y, what is that going to be equal to? Do we have any y's over there? No, we are just taking the derivative of a constant, right? X is just like a constant. So this is going to be equal to 0. What about round of n over round of x? What then? From this expression, if you take derivative, partial derivative with respect to x, and by taking partial derivative, I mean that assume that y and x are independent from each other. And if you are taking derivative with respect to y, then x is just a constant. If you are taking derivative with respect to x, y is just a constant. So what will happen here? From y, if I take the partial derivative with respect to x, Zero. Yes. If it was with respect to y, it was. And they are equal to each other, right? So what happens is this. This condition is satisfied. And this condition, if it is satisfied, I know that now my equation is exact. Now question is this. If I have this equation, and I do not know what is this function f, How can I find it? First of all, I need to know that this kind of a function exists, okay? If it exists, then we can dig up and try to find what's happening. Okay. For an equation to be exact, this is a necessary condition. But the question is this also a sufficient condition or not? Which means that if I am giving this equation and this equality is satisfied, can I be sure that a function like f exists such that if I take its derivative, I have that equation? Because if I have, then the level curves of that function is going to be my solutions. Okay? So, what is the idea then? The idea here is this. This equation that we have here, is also a sufficient condition. Why? Let's go with this. What do we have for our partial derivative of f with respect to x? We have this equal to n. What about partial derivative of f with respect to y? This is going to be equal to n. Okay. Assume that we have some clouds here, okay? And we do not see what is happening above. We only see this part of the equation. And I would like to find that function f, which I'm not seeing, but take it down and try to see with you what's happening. What should I do? The thing is this. When I'm taking the partial derivative of this function above the clouds with respect to x, I'm getting to this m. And when I'm taking this partial derivative with respect to y, I'm getting to this n. Is there a way such that I can recover that function f itself? Okay? This is exactly what we are going to do. First of all, if I take partial derivative of f with respect to x and get m, starting from here, can I say that my f is equal to integral of m with respect to x, assuming that all the y's that may appear here are behaving like constants, okay? And I need to add here what? Some constant of integration, right? This constant of integration, is it just going to be a constant? Yes, this is going to be a function of y actually. Because why? Take partial derivatives of this expression with respect to x. This is going to be round of f over round of x. From integral with respect to x, we are taking derivative with respect to x. So this is going to give us m plus, maybe I have a lot of terms that involve only y and they do not involve any x's. Since I'm taking the partial derivative with respect to x, they're all going to be 0, right? So if I do not take this as a function of y, maybe I'm going to miss some parts of the function. So that is why we are always saying that this is going to be a function of y. We can also start from here. We can write f as integral of n dy plus c, but that time, that c is going to be a function of x, the other value. Okay? What is happening here is this. We are taking these two assumptions, right? These two assumptions with the additional assumption that I have an exact equation, which means that this equality is satisfied. What is happening is this. I'm saying that I have a function f. I have taken the partial derivative of that function f with respect to x, and I have got this m. What does it mean for f? It means that f is going to be the integral of this with respect to x plus some constant, right? And that constant, since I was taking partial derivative with respect to x, those constants that may have some value of y, in this process of taking partial derivative with respect to x, they are all getting lost. So, in order for me to recover this, I need to say that, okay, this constant is also a function of y. Okay? What now happens? For the rest, what should I do? I'm using this, but I still have not used this assumption, right? What we are going to do is this. Take partial derivative of both hand side with respect to y. What is going to be the partial derivative of this with respect to y? This is going to be equal to n, right? N. I just wrote it. What about this hand side? This is partial derivative of this integral, because m is a function of x and y, and this expression may have some x and y included in it, and we can take partial derivative with respect to y. And if it does not have any y's, this is just going to be 0. But anyhow, what about this partial derivative of this cy? When I'm having a function of a single variable and I'm taking its partial derivative, it is exactly equivalent to taking the normal derivative. So this is actually d over dy, which I can also write it as c prime, right? So what is going to happen here? Let me just come here. Now, what's my c prime of y? My c prime is n minus round over round y of this integral. Okay? What was this? dc over dy, right? So I can write this as dc equal to n minus round over round y of m dx dy. Is it okay? And what I need to do is just take integrals, right? If I take the integral of this side and this side, from here I have c, which is going to be my c of y, and it is going to appear as this integral. But look at this. I'm going to be able to take integral of this expression if it is only a function of y, okay? In order for it to be a valid differential form, okay? So what we need to do, we need to be able to understand if this is only a function of y or not. How can I know this? If this is only a function of y, then its derivative with respect to x must be 0, right? Let's check it. Is derivative of this expression minus round over round y of integral of m dx, is this equal to 0 or not? So our question becomes this. Let me also clear here. I need my space. Is this or not? Let's just take partial derivatives. This is going to be round of n over round of x minus round 2 of I'm keeping this as it is minus. Here I can take and change the order of this mixed partial derivatives, right? So what is this going to be? This is going to be round over round y of integral of m dx. Look at this, round of n over round of x. What is this now? From a function, I'm taking integral with respect to x, then I'm taking its derivative with respect to x. What is this going to be? This is going to be m itself, right? So this is going to be round of m over round of y. Okay? But what is this expression equal to? What was our assumption, first assumption about, it is, yeah, exactly, it is equal to 0. What? Yes, if our equation is exact, which means that this equation is satisfied, then we have that equality over there, which means that this is equal to 0, which makes this partial derivative is equal to 0. And if it is equal to 0 with respect to x, which means that this function has no x in it. So here, I can take this integral with respect to y, and I am done with it. Okay? This is the general procedure in order to solve an exact equation. What we do normally is this. Let's solve some problems. Again, this equation. Yes, we know it is separable. Yes, we know it is an equation with homogeneous functions. We can solve it in many different ways. But let's try to solve it as this exact equations. This is our m. This is our n. Okay? Is this an exact equation or not?
It is.
It is. We have already calculated, and we know that this is an exact equation. Since this is an exact equation, this three-level things, f on the top, the equation, and the equality of mixed partial derivatives. Now I know that there is a function above the cloud such that if I take its derivative, I have this. I need to discover this function. How do I discover it? I start from here. What was the partial derivative of this function x, this function f with respect to x?
What?
It was the coefficient of the x, right? It was m. You remember? And what is our m?
What?
It is x. X, not 1.
But like, aren't we just taking the derivative?
From that function f, which I still don't know what it is, if I take derivative, partial derivative with respect to x, I come to this.
Yes. If you take partial derivative to x, it's not.
From m, if you take partial derivative with respect to x, yes. But I'm taking partial derivative with respect to x from the function f. We have this function f here. We have our equation here. Which is m and n. And I have what? Let me also write this. I have 1 of m over 1 of x, 1 of y.
So are we taking the y right now for x?
No. What is happening is this. Listen to me. What's happening is this. I have this equation, but I do not know this function. I'm trying to recover this function. Since if this is satisfied, then I know that this function exists. I'm trying to recover this function. How can I know it? I'm saying that, okay, if you take its partial derivative with respect to x, you have m. Partial derivative with respect to x is m. What is it here? It is x, right?
Yes.
So from here, what is my function f? It is integral of x with respect to x plus some constant which is a function of y, right? So what is happening here? What is going to be my f? My f is equal to x to the power of 2 divided by 2 plus a constant which is a function of y. Okay? We are taking integral, we are taking derivative, we are taking integral. This is the step-by-step procedure actually. Now, take derivatives with respect to y. What is going to happen? This is going to be round f over round y. What is the derivative of this with respect to y? The partial derivative of this expression with respect to y? This is 0 plus, what do I have? C prime of y or whatsoever. Okay? Now let's continue. What is round of f over round of y? To this equality, I do not know this, but I'm trying to find it, but I know this. And my round of f over round of y is equal to this n, which is here, y. So, c prime of y is equal to y. From here, what is my c? We need to just take integrals with respect to y, right? So it is going to be integral of this with respect to y. And we know for sure because of round of m over round of y equal to round of m over round of x. We know that this is only a function of y. And this is going to be y to the power of 2 divided by 2. I'm not adding the constant here right now because now I have covered my function f. And what is my function f? Which is a function of x and y. I had the parts that were related to x. I have x to the power of 2 divided by 2. And I had the other part, which was a function of y. And I was trying to discover that. And I discovered it. It is going to be y to the power of 2 divided by 2. So the solutions are the level curves of this function, which means that I can write it as x to the power of 2 plus y to the power of 2 equal to c. It is x to the power of 2 divided by 2 plus y to the power of 2 divided by 2 equal to c. But c is a constant, multiply both hand sides with a 2, and they can call that a constant. Okay? So the solutions for this equation is going to be this. Okay? That we have already developed. We are first taking the integral with respect to x, then take derivative, then take integral with respect to y. We can also do the same thing, but now instead of x, do this with y. Okay? If this kind of an equation is given to us, what is the procedure? What is the algorithmic way to approach these equations? In order to solve this equation, I need to do what? First of all, I need to understand what is the order of the equation. A general procedure, right? What is the order of this equation? This is a first order differential equation, okay? Is it separable or not? It is not separable. You can try it. Is there any expression like ax plus by plus c happening here? No, we do not see it. Is this an equation with homogeneous functions of the same degree or not? Is this a homogeneous function? Unfortunately, it's not. It is not. Yes. Because we have lambda x and we have lambda to the power of minus 1. We cannot take the factor out of it, so we can write the function itself. So that case is also not okay. So what is the next step in our ladder? To try to check if this equation is exact or it is not exact. What is our m here? First of all, let's decide on that and continue. It's the coefficient of dx. We normally call it m. So m here is y. Our function m of xy is y. What is our n? N is the coefficient of dy. So n of xy is actually x plus 2 divided by y. Okay? I need to check if this is exact or not. So the question is this. If it is exact or not, what should I do? I need to check that partial derivative of coefficient of dx with respect to y. And what is this? If you take partial derivative of y with respect to y, what are we going to get? 1. What about the partial derivative of n with respect to x? From this x we have 1 and we do not have x's here, so it is 0. So this is also equal to 1. Since this is equal, round of x, round of y, round of x, these are equal, we know that this equation is exact. Okay? This condition is satisfied. Now we know that there is this kind of a function such that if I take its partial derivative with respect to x, if I take partial derivative of that function with respect to x, I get m, which is y. And if I take partial derivative of that function with respect to y, I get n, x plus 2 divided by y. Okay? What should I do? Let me just have this removed from here to here. The question now turns into this. I have a function f. I took the partial derivative with respect to x and I got y. So what is the f? F is integral of this with respect to x plus c of, I'm taking integral, so this is going to be 1. Okay? So what is my f then? My f is going to be equal to, since we are taking partial derivatives, we are assuming that x and y are independent from each other. So this y in this integral is behaving like a constant. So I can take it out of the integral. Okay, so y times integral of dx. And what is that? Y times x. Or in alphabetical order, I can write this as xy. Okay? Plus c of y. Okay? What is the steps? Integrate, derivative, then again take the integrals. Okay? We have done one integration. Let's take derivatives. But now with respect to what? Now with respect to y. Because I need to have partial derivative of f with respect to y, so I can use this expression. If we take partial derivatives with respect to y, what do I have? Partial derivative of f with respect to y, which is equal to x plus 2 divided by y. This is going to be equal to, take partial derivative of this with respect to y, x, and partial derivative of a single valued function with respect to y. This is going to be the derivative of this, okay? C prime of y. And here by C prime I mean derivative with respect to y. Okay? Good? Now, what happens? What do you see? This x and this x cancel, right? So C prime of y is equal to 2 divided by y. We have taken the derivative, now it's time for the second integration, right? Now, C of y is going to be equal to what? If derivative is equal to this, the function itself is equal to the integral of this, right? Integral of 2 divided by y dy. And this is going to be equal to what? 2 ln of absolute value. Again, I'm not writing c here because let's just keep it. So from here, what is our function fxy? I have been able to discover one part of it. And in this step, I have covered the rest. And it is 2 ln of absolute value of y. So the solution for this equation is going to be the level curves of this function, which means that solutions are, let me continue from here. Solutions are xy plus 2 times ln of absolute value of y equal to c. Done. We can also do the exact same thing, but instead of starting with this, we can start with this one. Why not? Let's also try that. I'm just deleting everything. Is it okay for me to clean? Okay. What are these steps? Integrate, derivative, integration. Again, I'm not keeping them in harmony, but anyhow. Okay, so let's start from this one, this time. There is this function f such that when I'm taking partial derivative with respect to y, I get to this expression. Which means that I'm assuming y and x are just independent from each other. So what is f? F is going to be integral of what? X plus 2 divided by y. Shall I write dy over here or dx over here? What was this? This is derivative of f, partial derivative of f with respect to y, right? So in order to go back to f, I need to take the integral with respect to y. So this is dy. And this is our second solution for the same equation. Plus, now I'm going to add a constant c, but this is a function of y or x. This is going to be a function of x. Okay, good? Now, can you please calculate this integral? from here, my f is, x is just a constant. Take it out. This is the only case that you are assuming x and y are independent from each other. In all other cases, if you, for instance, when you were working with the separable equations, if you had this kind of a thing, you were saying that, okay, this was not a valid differential for, because you were assuming that y is also a function of x. But since here, y and x are coming from partial derivatives, and you're assuming that when you're taking partial derivatives, those are independent from each other, then now in the integration I can also assume that x is behaving like a constant, okay? So take the constant out, integral of dy, y, yes, y, plus 2 times integral of 1 divided by ln of y plus c of x, okay? We have done one integration. What is the next step? To take derivatives, right? To come back again. But this time I'm going to take derivatives with respect to what? X here, right? X. Because I have used round of f over round of y, but I haven't yet used this. So I need to take derivative with respect to x, so that I can also use this equality. By taking derivatives with respect to x, I have round of f over round of x, which is equal to y. What is the partial derivative of this expression with respect to x? xy's derivative, and we are assuming that y is just a constant. So it is just going to be y plus, from this expression, if you take derivative with respect to x, what will we get? 0 plus c prime of x. What do we have here now? This y and y cancel. So what I have is this c prime of x is equal to 0. What does this mean? It means that this c prime, this c of x, is just a constant. Okay? I call it a. So what is going to happen? What is going to be my function? My function f is going to be xy plus 2 ln of y plus this constant. Since my solutions are going to be level curves, if I also add this constant, I will take it to the other side and just rename it as another constant. So there is no need to add this. So after recovering this, what my solutions are going to look like? It is xy plus 2 times. It is exactly the same. Okay? X to the power of y plus 2y dy equal to 0. You are given this differential equation. Can you please solve it? Or what are the questions that we are going to ask ourselves? What? E to the power of y dx plus x e to the power of y plus 2y dy. Okay? What is the first question that you need to ask? The first question you need to ask is this. Is this separable or not? We know it is first order. Is this separable or not? It is not. Are we working with a function such that it has this expression ax plus by plus c? No, we do not have. Pass it. Are we working with an equation such that has this homogeneous functions in it of the same degree? Are they homogeneous functions? No, they are not. So again, pass. What is the next step in this ladder? Is this equation exact or not? First, check that if it is exact. Then, if it is exact, what should we do? We integrate, take derivative, again integrate, right? This is the steps. What is our m here? Yes, the coefficient of dx. What is our n here? The coefficient of dx. Can you please calculate this? And round up n over all, what are these? Can you please calculate them? Okay. If we are taking the partial derivative of m with respect to y, what we are going to get? E to the power of y's derivative. What is the partial derivative of e to the power? Can you please stop? Hemen nereye konuşmaya başladı? Bitirin lütfen. Okay. We have this differential equation. We need to first understand if it is exact or not. If it is exact, then we integrate, take derivative, integrate, and we have the solution. So let's check if this is exact or not. Take the derivative of e to the power of y with respect to y. What is e to the power of y's derivative with respect to the y? E to the power of y. Yes. What is this n's derivative with respect to x? X e to the power of y's derivative. E to the power of y is just a constant, and so it is going to be e to the power of y. Plus 2y's derivative. 2y is also a constant, and if you are taking the derivative with respect to x, partial derivative, it is 0. And these are equal to each other. Since these are equal to each other, we are sure that there exists such function f such that its derivative is equal to those things. What does this mean? This means that there is this function f such that if I take its partial derivative with respect to x, I get m. And what is my m here? E to the power of y. And if I take partial derivative with respect to y, I get n. And what is my n here? X e to the power of y plus 2y. Okay? Now what happens? Again, we are going to write exactly the same things. These 3 steps. And what are these 3 steps? First of all, let's start from here. If I have taken the partial derivative of f with respect to x, and I have got e to the power of y, then f is integral of e to the power of y with respect to x, by assuming that y and x are independent variables from each other. So this is going to be f equal to integral of e to the power of y dx plus c of y. What is this integral? E to the power of y is just a constant, right? Take it out, and integral of dx is x. So this is going to be x e to the power of 1 plus cy. Y is just a constant. So e to the power of y is also a constant. So I can take it out of integral. The constant can get out of integral, right? The linear property of integral. So I'm having e to the power of y integral of dx. What is integral of dx? X. Right? X plus c, but not c. Okay? So what do we have here? X e to the power of y plus c of y. Okay? We took one integral. Now we are going to take a derivative. Then again we are going to take another integral. Can you please take derivative? But with respect to what? Y. Yes. What is the partial derivative of f with respect to y? This function n, right? Or this one. This is going to be, if I take partial derivative with respect to y, this is going to be round of f over round of y. And instead of that, I'm just going to write x e to the power of y plus 2y equal to. What is the partial derivative of this expression with respect to y? And we're assuming x is just a constant. So x is just going to be x e to the power of y. Plus, this is a single variable function. Partial derivative with respect to y is the normal derivative. So it is going to be c prime of y. Now make that cancellations. This is going to be cancelled by this. So what do we have? Derivative of this function c with respect to y is 2 times y. What is our cy then? It is integral of 2y dy, which is equal to what? 5 to the power of 2. Plus c, but let's keep that for now. So what is going to be our function f? What is our fxy? Our fxy is this x e to the power of y plus the cy, right? And what was the cy we calculated? 5 to the power of 2. So the solutions for this differential equation are going to be the level curves of this function. So x e to the power of y plus 1 to the power of 2 is equal to c. Okay? These are the solutions. How can we be sure about it? Just do the reverse thing. If from this you take partial derivative with respect to x, you will see that m is going to appear. And if you take partial derivative with respect to y, you will see that this n is going to appear. So we have already found the correct solution. Okay? This was the first way. We also have another second way to approach this problem, right? What can we do? Instead of starting from this equation and then using this, we can use this one. We can start with this one and then use this one. Let's go over it. If I take partial derivative of f with respect to y and I come to this expression, then f is going to be integral of this expression x e to the power of y plus 2y with respect to y plus a function of x, right? If derivative with respect to y is this, then f is integral of this with respect to y plus that constant which is a function of the other variable x. Okay? Let's do the calculation. What is our f then? From x e to the power of y, we are taking integral with this assumption that x is just a constant. So we have x coming out of the integral, we have integral of e to the power of y. And it is e to the power of y. Plus, what is the integral of 2y? Y squared. Plus this c of x. Okay? First step is done. Integration. The second step is taking the derivative, but with respect to x. So if we take derivatives with respect to x, I'm going to have round of f over round of x on the left hand side of this equation. And what is round of f over round of x? It is e to the power of y. This is going to be equal to, what is the derivative of this expression with respect to x? E to the power of 1. Plus, what is the derivative of this with respect to x? 0. And we have c prime of x. Now we have this e to the power of y, e to the power of y cancelling. C prime of x is 0. What is c of x then? Just a constant. Let's call it a, or b, or c, or whatsoever that you would like. Okay? Now, what happens to our function? Our function is x e to the power of y plus y squared. I know it from here. And this constant, right? We can write that constant. We can get rid of that constant. Here it doesn't matter for me because I'm interested in the solutions, not in the function. And solutions are appearing as level curves of this function. So this is my solution. So both ways, they're leading to the same solution. Okay? It doesn't matter from where you continue. Start from this and try to see which one of these integrals are easier to handle. Then continue that way. Okay? Good. Can you please try to solve this differential equation? What are the questions that we ask ourselves? when we are dealing with a differential equation that's looking like this.
What's m and what's n?
No, first of all, what is the order of the differential equation? This is the first order differential equation. So the next question is that, is it separable or not?
It's not.
It is not separable. What is the next question then?
Is it exact or not?
No.
Is there a range of x equals to xy plus ey plus a? No, that's too much. Homogeneous.
We have z equal to f of ax plus by plus c. Do we have any linear expressions? No, we do not have. The next question is this. Do I have this equation such that functions are appearing as homogeneous of the same degree or not? No, unfortunately it is also not that. What is the next question? Is it exact or not? The next question is this. Is this an exact equation or not, right? For it to be exact, we need to check, first of all, what is our m, what is our n, and then their partial derivatives. Try to see if they are matching together, if they are equal or not. What is our m here? M is the coefficient of dx, right? So this is m, and this is n. What is partial derivative of m with respect to y? From the coefficient of dx, we are taking derivative with respect to y. What is this going to be? 2y. Yes, 2y. What about root of n over... I'm writing very bad n's. They're not very beautiful. Root of n over root of x. And what is this? Minus 2y. Are they equal? No, they are not equal. Which means that this question, this differential equation is not exact. What should we do? Make it exact. Exactly. I'm taking something out from my pocket and I'm saying that multiply both sides of this equation with 1 over x to the power of 2. What is happening there? What we are going to have? Let me also check. Yes. Can you please multiply this equation with 1 over x to the power of 2? This is going to become 1 over x plus y squared x squared dx minus 2 times y divided by x dy equal to 0. Is it right? Now, can you please check that if this equation is exact or not? Again, we need to take this m, we take this as n. What is wrong with m? Let me call this m tilde and n tilde also. Over with y. What is this going to be? Right? What is root of n tilde over root of x? This minus 2y, you keep it. What is the derivative of 1 over x? This x to the power of minus 1 is derivative, right? So that minus 1 is going to come as coefficient. So this is going to be plus. And we make minus 1 minus 1. So it's going to be minus 2. Bring it down. Okay? So what happened now? The thing that happened is this. Now I have an exact equation. I have been able to turn this equation, which was not exact, into an exact equation. What are the differences between these two? Now I can say that I know there is a function f such that if I take its partial derivative with respect to x, I get this. If I take its partial derivative with respect to y, I get this. But for this equation, I cannot say something like that. Okay? Now problem turns really into this. How can I turn a problem which is not exact by multiplying it into something such that it becomes an exact equation. This is what we are going to discuss. But first of all, I need to give some explanation. Let's define something like this. When I'm writing, let's start with this. We can write this as dy over dx as equal to minus n over n, right? Assume that now I'm considering this y and this x as functions of time, t. What do I mean by this? I mean that, assume that I have this xy plane, okay, such that derivative of x with respect to time, dx over dt, is equal to n, and derivative of y with respect to time, dy over dt, is equal to minus n. Okay? These are some kind of equivalent formalization of the same problem, but I'm trying to turn this into a geometric case. So if you remember from other courses, we have talked about the phase spaces, right? In which you have that vector field attached to each point of this space, and we are trying to see what is happening here. This is exactly the same situation. Okay, for any point that you take in this space, let's say this point I take, I have its velocity vector attached to it with respect to time. Okay? In the direction of x, the velocity vector is going to change with this. The velocity vector in direction of y is going to change with this. Okay? So for instance, it's going to be like this. Then I will come to this point. I again calculate that derivative. Go on, come here, go on, come here, go on, come here, and so on and so on and so on. Okay? I haven't yet talked about uniqueness and existence of the solutions theorem, because you're engineering and you do not care about them. But when we are going to talk about numerical solutions of differential equations, I'm going to come back to this point. Okay? But what is happening is this. We are having a lot of ways and paths. For instance, this is one of the trajectories. If I'm having a particle moving here, it has x, it has y coordinates, right? From here, I'm able to see the x coordinate of its derivative and the y coordinates of its derivative, okay? And if I'm able to see all of its derivatives in all directions at all of the points, and if I follow that along that trajectory, what I'm going to see is that this path that is happening here, okay? It's called a trajectory. Or it can move like this, or it can move like this, or it can move like this, or many, many, many different things. Depending on what is your initial condition, what is your initial starting point, you may be on some different trajectories, right? They are possible. In nonlinear case, they are possible. What do you mean by it's not possible?
For 1x, there's 2y in a 1 point.
It is not a function here. This is a function of t, this is a function of t. Okay?
So if we are calling it functional, is it like
if you draw this, then it is going to be something like this. If you are drawing y, t, it is maybe going to be something like this, okay? These are both functions. But I'm drawing here y with respect to x, y against x. Not the other way. Okay? They are parametrized curves that you are seeing here. What do you mean by that?
What I'm trying to, for example, x5 is having two, like,
x5?
for example, sen x5 diye düşünürsek yerine hani iki noktada kesiyor ya, onun nedeni bağımsız olmalı.
I'm not saying here that y is a function of x. If I'm saying y is a function, I'm just saying that I have a curve, I have a trajectory in the plane, and I'm parameterizing it. And that parameterization, the x coordinate of that curve is going to come from x of t, and y coordinate is going to come from y of t. Yes, x is a function of t, y is a function of t. But it doesn't mean that necessarily y is a function of x, so that it's not going to come. I'm just looking at the trajectories. Okay? Anyhow, the problem is that when you're having this vector field, okay, you see for instance here. When we are finding the solutions for this differential equations, actually we are given with these vectors, with these speeds, and you're interested to understand what is this path, what is the trajectory that our particles are going to take, okay? I can change the speed, right? I can, for instance, multiply this with 5 and with this 5, okay? I can stretch this velocity vectors, but as long as I'm not changing their direction, or I'm changing it constantly, in such a way that trajectories are again the same, but the trajectories are going to be traversed with different speeds, okay? I am not actually changing my system of this movement of the particle. So I can also say that, okay, if I multiply this with a function mu, okay? As long as there is this consistency conditions and so on, let's just pass over it. You engineers don't care it. I also don't care about it, okay? As long as I'm able to change the speeds in such a way that the trajectories remain the same, I'm working with exactly the same system, okay? This is the geometric intuition behind what we call integrating factors. Okay, what is an integrating factor? Let me come here and explain it. I don't have a lot of place, so it's better to keep on. Let's assume that we have this m dx plus n dy equal to 0. Okay? But it is not an exact equation. What we are after is this. Can I multiply this equation with a function mu, which is a function of xy, such that after multiplication, this equation becomes an exact equation or not? If I can find this kind of functions, then those are called integrating factors. And we just multiply the equation with that. This turns that equation into an exact equation, so we can solve the equation. But how can we find these integrating factors? Look at this. If you assume that this equation is exact, what does it mean? It means that the condition for exactness must be satisfied, right? What was the condition for exactness? That derivative of this, derivative of coefficient of dx with respect to y, mu m or mu m, this must be equal to what? Derivative of coefficient of dy with respect to x. N. Okay? Let's expand this. We have multiplication of two functions, right? Derivative of the first one times the second one plus derivative of the second one times first one. So this is going to be m root of mu over root of 1 plus mu over root of y. This is for the left hand side. What about the right hand side? Again the same thing. N root of mu over root of x plus mu times root of n over root of x. Okay? if our mu, this integrating factor, was just 1, okay, which means that our original equation was actually exact, what would have happened? Derivative of 1 with respect to y is 0. This gone, mu is equal to 1. So from here we have round of m over round of y equal to, again, this is 0 plus 1 times round of f over round of x. So the condition for exactness was true. If it was an exact equation for mu equal to 1 before coming to this point. Anyhow, we are trying to make this into an exact equation. So this equality must be satisfied. Okay? Let's collect all the terms such that we have mu to one hand side and the rest to the other hand. So this is going to be mu times minus n over x equal to, what do I have here? N round of mu over round of x minus m times of mu over round of y. Okay? Now, here we have some cases. Let's call this equation as equation star. Case 1. If what does this mean? This means that my mu, my integrating factor, my mu, is only a function of x. Is only a function of x. Then what happens to star? I have this mu of x, round of n over round of y, minus round of n over round of x. Okay? This is going to be equal to what? What happens to this one? If our mu is only a function of x, then we are taking its derivative with respect to y, then this is going to be 0, right? So what is going to happen? This is going to be n times derivative of mu with respect to x, and since this is only a function of x, so this I can write this as d over dx. Good? Please.
For the mu x and then in practice, partial differentiation of m over partial differentiation. Yeah, the first one. Won't that be 0 to? Yeah.
Is this equal to 0, you say?
No, the one with respect to y.
This
Yeah.
with respect to y? Okay.
Won't it be 0 since it's also only the function of x?
No. We are not talking about m. We are talking about mu. This must be a, you see, my assumption is that this integrating factor is only a function of x. Okay? So what happens here? I can write this as d mu over mu equal to round of f over round of y minus round of n over round of x divided by n dx. Okay? We said that this is only a function of x, right? So my assumption is going to be like that. This is also a function of x. Let's call it p of x. Okay? Now what do I have here? I have a separated equation, right? So I can write that ln of mu is equal to integral of px dx. From here, my integrating factor is going to be e to the power of integral of px dx. So what is important here for us? It is this one. Okay? So let me note it here. D. It is actually round of over round of x, but since we assume that mu is only a function of x, the partial derivative is equal to the normal derivative. So, okay. If round of f over round of y minus round of n over round of x divided by n is only a function of x, then if you multiply this equation with this expression, then you are going to turn that non-exact equation into an exact equation. Okay? My second case here can be this. Yes.
Then we were writing in the right up.
Okay.
We were writing it wrong. How
This.
Yes. How we could say that when we had that dx is gonna directly equal to the mu right minus, because like in inside it's wrong though, but in outside.
Okay. From n I'm taking partial derivative with respect to y. It has nothing to do with mu. M and n are functions of x and y, possibly. So I can talk about their partial derivative with respect to x and y. But my assumption here is that this integrating factor is going to be only a function of x. With this assumption, I can write this as this. And it means that if this is only a function of x, I can calculate mu as this. Okay? My case 2 is going to be this. If mu is going to be only a function of y, then what happens? Then you can again write these things, but this time this is going to be, since there is no y in mu, this is going to be equal to 0. So this is going to be minus m d mu over dy. And also I need to write this as function of y. Okay? This is going to be exactly the same thing, but this is going to be minus m, this is dy, and if this is a function of y, then I'm done with it. Okay? If all of them over on y minus then there is also another case that I'm going to leave it for you. If my minus mx, or let me write this as if this expression is going to be a function of x times y, then our mu is going to be e to the power of integral of f of z. Try to check this from what we have written here. Try to see if you can figure it out why it is like that. But the problem is this. I myself don't even remember this. Okay? I also don't remember this. I have tried to memorize it, not to, but you're just going to forget them. Don't worry about them. I'm also just going to talk about something more, that if you want to get it, then there is no need to go check this. But these two are going to be useful for us. At least you need to be aware of these two. If you can memorize them, memorize them. But I do not recommend it, because I myself have not memorized it. Whenever I need them, I can just write and drive it. It is a little bit taking more time, but at least there is no need to memorize anything. Anyhow, but these two are important for us. Let's see some examples. It will make it much more clear. What can I have? Okay. Y dx plus x to the power of 2y minus x dy equal to 0. If we are given this equation, how can we solve it? Again, we need to ask the same questions again and again, right? If it is first order, yes. If it is separable or not, no, it is not separable. There is no linear term. The functions are not homogeneous. So, what is the next question? Is it exact or not? Can you please check that if this differential equation is exact or not? What is our m? What is our m? Is y. This is our m. What is round of m over round of y? This is 1. What about round of n over round of x? 2xy minus 1. Are they equal?
No.
No, they are not equal. Which means that this is not an exact equation. So I'm stuck. So what is the next step? Okay, exactly. We need to turn the problem into a problem. We know how to solve it, right? So we are going to look for an integrating factor. If we can find this integrating factor, we just multiply it and try to see if this turns into an exact equation or not. But how can we find this integrating factor? We need to check this one, and maybe this one. I always check this one, and the rest I do some other trick that I'm going to show it to you. Because this is humongous to remember and useless. And to be honest, remembering all of these things is going to be super useless. So just this 2 is going to be enough. Okay. Let's check this. First of all, I need to calculate round of m over round of y minus round of n over round of x divided by what? N. And I'm going to see if this is a function of x or not. If it is a function of x only, then I'm going to be able to find an integrating factor. Let's write it. What is this going to be? 1 minus this. So this is going to be 2 plus that. And I also take a factor out of. Is this right? No, it is not right. Definitely it's not right. 1 minus 1 is 2, but this is as a minus as well. This is 2 times 1 minus x1. Now I think this is true. Good? Isn't it? Let me write this step. 1 minus 2xy minus 1. We have it here, we have it here. So it's going to be 2 minus this, and I'm getting a factor out of it. So it is 2 times 1 minus xy. Can it be divided by n? And what is our n? X to the power of 2y minus x. Yes, we need to take a factor out of x's. So this is going to be 2, 1 minus xy. X, let's take a factor from minus x. So this is going to be 1 minus xy. Right? These are cancelling, and what we have? We have minus 2 divided by x. Is this only a function of x? Do we have any y's here? No, we don't have any. So this is only a function of x. So our integrating factor is going to be what? E to the power of integral of minus 2 divided by x dx. And what is this going to be?
Minus 2 ln.
E to the power of minus 2 ln of x. I'm dropping absolute values. And that's c. Yes, this is going to be minus 2 to the power of x. And e to the power of ln, those are the inverse functions. So this is going to become e to the power of ln of x to the power of minus 2. I don't know if I'm writing it small so you can see, please let me know. And this is going to be x to the power of minus 2, or 1 over x to the power of 2. Okay? Now, can you please multiply this equation with 1 divided by x to the power of 2 and check if it is exact or not? Let's do it. I need some more space, so I'm just going to erase all of these. Y divided by x dx plus y minus 1 over x dy. If I multiply this equation with 1 over x2, it becomes this, right? Can you please check that if this is an exact equation or not? Let's solve it. We had that problem, but it was not exact. We tried to find some integrating factor, we found it and multiplied it. We must be sure that it is exact. It has turned into an exact equation. So how can we check it? Just take the derivative of coefficient of the x with respect to y. And this is going to be 1 divided by x2. Because x is just a constant, so the coefficient of y is 1. And from here, we need to calculate the partial derivative with respect to x. Y is 0, because minus 1 over x is derivative, partial derivative with respect to x, or derivative with respect to x is minus 1 over x to the power of 2. So it is 1 over x to the power of 2. Okay? And this equality is satisfied. It means that this is an exact equation. So how can we solve it? We know that there is this function f such that if I take its partial derivative with respect to x, I have y divided by x squared. Then I take its derivative, partial derivative with respect to y, I have y minus 1 over x. Okay? So we can start finding f either by this one or this one. Whatever you like, it doesn't matter. Let's start from here. So f is going to be integral of y divided by x2 dx plus c of y. So f is going to be equal to, what is this integral? Y is a constant, get it out, and this is x to the power of minus 2. So we add 1 to the exponent and divide everything by the exponent. So it's going to be minus y divided by x plus c of y. The first step was integrating. Done. The second step is taking the derivative, but with respect to the other variable y. So we have y minus 1 over x as the partial derivative of f with respect to y. Partial derivative of this with respect to y is minus 1 over x, and we have the derivative of this. Okay? These two cancel each other. C prime of y is y. So c of y is going to be integral of y dy, which is going to be y to the power of 2 divided by 2. Plus that c falan, but so what is our xy? F of xy, our f is equal to this minus 1 over x plus what? Y to the power of 2 divided by 2. So what is our solutions? Our solutions come as level curves of this function. So solutions are going to be minus y over x plus y to the power of 2 divided by 2 equal to c. Done. Okay? Now question. Can you please start from this expression? Take the integral with respect to y, take the derivative with respect to x, and do it. Can you please also do it? Okay. When I'm trying to solve an exact equation, what I'm doing, when you have an exact equation, when you are starting to solve the equation, okay, try to find that function f. When we are trying to find that function f, we start from either of these equalities, right? And we first do what? We are taking this, for instance. Integrate. Okay. Here take derivative. Again do what? Integration. Integrate. It's starting from this one. But who says that I have to start with this one? I can start with this one as well, right? So let's do it. It's like that. I'm saying that I have this function f because I am sure about the existence of that function f, because this is an exact equation. If I'm taking partial derivative of that function with respect to y, I'm getting this. So f is equal to integral of this with respect to y. F is equal to integral of y minus 1 over x dy plus a constant, a coefficient of integration, constant of integration, which is a function of x itself. Okay? So this is our first step, integration. Let's do the integration. So f is going to become what? This is y squared divided by 2 minus y divided by x plus c of x. Okay? Integration step is done. Now we are going to take the second step, which is taking derivatives with respect to this variable x. What is partial derivative of f with respect to x? Partial derivative of f with respect to x. Now I have it here. Y divided by x squared equal to. If I take partial derivative of this expression with respect to x, it is 0. What about this? Just take y and minus also 1 over x's derivative is minus 1 over x to the power of 2. So you have this plus c prime of x. Okay? What happens? These cancel. So what do I have? I have c prime of x equal to 0. Now I need to integrate, right, in order to come to the c. And if you integrate, what do we have? The c of x is a constant. It's called a or whatsoever. Okay? So what is going to be my function f? My function fxy is, I have found this part, y to the power of 2 divided by 2 minus y divided by x plus that constant. I don't care about it. So what are my solutions? My solutions are going to appear as level curves of this function. So y to the power of 2 divided by 2 minus y divided by x equal to c. And those are going to be my solutions. And this is exactly the same thing that we found over there. Right? Good? We have this differential equation. We need to do what? We need to solve it, right? So what are these steps?
Is it first order?
Yes. And when we understand that it is a first order differential equation, we need to ask this question. Is it separable or not? It seems not. Pass. Is there any expression like ax plus by plus c that, again, no, we have nonlinear terms here. Pass. Is this equation an equation which involves functions which are homogeneous of the same degree? Unfortunately, again, no. So pass. The next question is this equation exact or not? It is not exact, actually, yes. Can you find an integrating factor such that makes this an exact equation or not? What? Minus? Okay, good. I don't know, we'll check it. Can you please multiply it and try to see if it is working or not? But someone can ask you from where you are getting that, right? So can you please write that? We had 2-3 expressions like, we were checking if it is a function of x, then this is an integrating factor. If it is a function of y, then it is an integrating factor, and so on and so on and so on. Can you please check that? This is my m. This is my n, okay? I need to check what? Round of x over round of y minus round of n over round of x divided by, it was n, right? What about this?
X minus 1 over x.
Round of x over round of y. This is 1 plus 2xy. Y, x, y squared. Okay? Minus derivative of this with respect to x, it is going to be minus 1. What about minus x? This is going to be 2 plus 2xy divided by minus x. Is this only a function of x or not?
No, it's not.
It is not. So it didn't work. We need to check the other option. And what was that? In order to just round of x over round of y minus round of n over round of x minus m. Was it minus m? Can you please just remind me this? It was minus m, right?
It was over m and x function of x.
Yes, I need to also check if this is a function of y or not. Okay, so what is this? I have already calculated that. So it is 2 plus 2 times xy. And what is minus m? Minus m is minus y. 1 plus xy. We can also take a factor out from this 2. So it is going to be 1 plus this. Okay? These two cancel out, and yes, Fahad, you were right. It is minus 12. Is this only a function of y or not? Yes, it is. So our integrating factor mu of y is going to be equal to what? E to the power of integral of this. Minus 2 divided by y dy. And this is going to be e to the power of ln of y to the power of minus 2, which is going to be e to the power of minus 2, which is 1 over y squared. Okay? Now, can you please multiply this equation with this integrating factor, check if it is exist or not, if it is exact or not, and if it is exact, can you please solve it? So what is going to be our equation? Our equation is going to be 1 divided by y plus x divided by x dx minus x divided by y to the power of 2 divided. Now, is this an exact equation or not? It is exact, right? Can you please solve it? So if this is an exact equation, what do we have? We are sure that there exists this function f such that if I take its partial derivative with respect to x, I get this L tilde, which is going to be x plus 1 over y. And if I take its partial derivative with respect to y, I'm going to get this expression, minus x by the power of 2. Now, can you do this integration, taking derivative integration in order to figure out what is f? Okay, let's solve it. What I need to do, I need to just put the pieces of puzzle together, right? If the derivative of f with respect to x is this, then f is equal to integral of that expression, indefinite integral of that expression, with respect to x plus g of y. From here, what do I have? F is equal to x to the power of 2 divided by 2 plus x divided by y plus c of y. Now take partial derivatives with respect to y. So the left hand side is partial derivative of f with respect to y, which is minus x divided by y squared, which is equal to partial derivative of with respect to x with respect to y, is 0. Partial derivative of this with respect to y is again minus x, right? The power of 2 plus c prime of y. These cancel. What do I have here? C prime of y is equal to 0. What does this mean? C, which is a function of y, is actually a constant. Okay? A. Now, come back and place it here. Because I'm going to work with the level curves, there is no need for me to add that constant here. Because if I write that equation f of x y equal to c, I can take that to the other hand and just rename it. So, f of xy is going to be x to the power of 2 divided by 2 plus x divided by y plus that constant, this constant here, and let's choose it as equal to 0. It doesn't make it less general. So the solutions are going to be x2 divided by plus x divided by y equal to c. Okay? Can you please find an integrating factor for this non-exact equation? What we need to do? Round of f over round of y minus round of n over round of x. Divided by n. If it is a function of x, then our mu is e to the power of integral of that function, that expression which was a function of x dx. For y as well, for xy as well, and you know, a lot of motionary. We can show that if a non-exact equation has at least one integrating factor, then it has infinitely many integrating factors as well. So you can also come up with different integrating factors, right? But the thing is that among these infinitely many integrating factors, which one of them we are going to find? If I write that expression and it's not a function of x, the second expression and it is not a function of y, the third expression it is not a function of xy, what should I do then?
Will we use the useless case?
The useless case, what do you mean by that?
The ones that you told us it's useless.
Yes. To be honest, integrating factors are all useless. But they're good in, you know, in church of mathematics, it is really glorified that, okay, this is a very good way to solve, but yeah, you know. Anyhow, my personal trick that I like is this. Let's assume that our integrating factor mu is coming like this. X to the power of alpha, y to the power of beta. Okay? We assume that this kind of an integrating factor exists. Okay? Then multiply this equation with this expression. Okay? Check the condition for exactness, and from that condition, find alpha and beta. With this way, you can come up with an integrating factor, right? How can we do it? Let's check. If you multiply this equation with this expression, what do I have here? I have 2y multiplied by this, so it is x to the power of alpha, y to the power of beta plus 1. Right? I have a y here, and another y to the power of beta are coming from here. Minus 3 times x, y to the power of 2, right? So it is minus 3 times 1x from here, alpha x from here, and I have y to the power of 2 here, so it is y beta plus 2. Okay? This is what our dx. I need to just break this boundary. Minus. Multiply it with what? With this one, right? X to the power of alpha plus 1, y to the power of beta, dy equal to 0. Okay? We assumed that by multiplying this equation by this expression, we have an exact equation. Okay? So our assumption is what? This is an exact equation. So derivative of the coefficient of dx with respect to y, let's call this m, and this has n. Then round of f over round of y must be equal to derivative of this with respect to x. What is this?
May I ask something?
Yes, please.
I missed the whole point about how we write m and n.
What do you mean by that?
I mean, like how we said x, 2x, power of alpha, y power of beta.
Look at this. What we have here, y 2 minus 3xy, right? Just 2y minus 3xy to the power of 2, right?
Yes.
Now I'm multiplying this whole thing with what? X to the power of alpha, y to the power of beta. This is multiplied to this one. 2x to the power of alpha, y to the power of beta, 1. Minus 3x, 1 and alpha plus 1. Y to beta plus 2. Good? And that is exactly the same thing. Okay.
Excuse me, sir.
Yes, please.
Where did the qx, the alpha, the number?
This see, I have this whole thing here, and I'm multiplying it with this expression. This is 2y minus 3xy cubed, right? What I have written here. I'm assume that my integrating factor is in this form. So multiply it with the equation. Okay? And since we assume that it is an integrating factor, it means that I'm getting an exact equation. So my assumption is that this is an exact equation. And what is the meaning of that? This derivative must be equal to the n's partial derivative with respect to x. So let's calculate it. What is this derivative with respect to y? I have 2, this beta plus 1 is going to come. X to the power of alpha, y to the power of beta. Okay? Minus 3 times, now we have beta plus 2, x to the power of alpha plus 1, y to the power of beta plus 1. Right? This must be equal to, let me write it in another color. This must be equal to what? Round of n over round of x, right? And what is that? If you take the partial derivative of this expression with respect to x.
The power of alpha plus 1 multiplied by y power of beta minus 1.
If what you were saying is this, you're right. Otherwise, no. Good? So what happens here? What should I do for the rest? Look at this. Do I need this one here? No. Just ignore it, don't see it. We have this equality here. This one here. For which values of alpha and beta do I have this equality? Do I have any x to the power of alpha plus 1, y to the power of beta plus 1 in this hand?
No, so it will be 0.
We do not have it, right? Or the coefficient of x to the power of alpha plus 1, y to the power of beta plus 1 in this right hand side, it is equal to 0. So this coefficient must be 0. So from here,
Can we say that beta equals to minus 2?
yes, of course, because this is 0, and from here we have beta equal to minus 2. Okay? What about alpha? Now look at this. Since beta is equal to minus 2, we actually do not have this. We can get rid of this. Let's get rid of that. Okay? Now, we have x to the power of alpha, y to the power of beta, x to the power of alpha, y to the power of beta. Their coefficients must be equal to each other. What is the coefficient in this hand? In the left hand side? Beta was minus 2, 1, right? Minus 2 plus 1 is minus 1, right? Minus 2. So, minus 2, the coefficient of x alpha y beta in the left hand side must be equal to the coefficient of x alpha y beta in the right hand side here. So this is also like minus alpha plus 1. And from here you can get that alpha is equal to what? 1. So what is the point of this? It means that mu of xy equal to x y to the power of minus 2 or x y squared is actually an integrating factor for this equation. Okay? Now, as the exercise, please multiply this equation with this integrating factor. Check that it is really an exact equation, and since you have an exact equation, please solve it. Find that function fxy. Okay? Do you have any questions? Up to now.
Think for all.
What do you mean?
For this.
Yes, it may work for almost all of the cases.
So it's can like understand this. We can not.
Yes, of course, of course. But if you are not saying that, okay, these kind of calculations are boring or a little bit complicated for me, yes, of course, definitely use this.
Because it's only one.
Yes. Keep safe and see you next week. Bye bye.